If you have ever used the synchronized keyword just to increment a number, you might be doing more work than you actually need. Synchronized is great for protecting large blocks of the code, but for simple updates like counters, flags, or swapping references, it is often overkill. There is a lighter, faster way, and it lives inside concurrent atomic package. Today, we are going to go through this package step by step, and by the end, you will know exactly which atomic class to reach for, whether you are building high performance counter, managing a pool of connections, or even updating fields in legacy code without changing a single line of it. The atomic package is not a random collection of classes. It is organized into 5 clear groups, and today we'll understand first 3 of them. The first group handles single values like integer, long, boolean, or object references. And the second group handles individual elements inside an array. And the third group uses reflection to handle fields on existing objects. Before we look at each group, we need to quickly understand the engine that powers all of them. It's called compare and swap. Here is a recap of how it works in plain terms. When you want to update a variable, you first read its current value. You perform your calculations, and right before you write a new value, you check one last time and you ask, is the current value still the same as what I read earlier? If it is, you write the new value. If it is not, then that means some other thread changed it in the meantime. So you simply read the new value and try again. This is a loop. It is non-blocking and it is fast, and it is the foundation of everything we are about to discuss. One important rule before we start: all of these atomic classes give you volatile memory semantics. That means any read you do always fetches the fresh value from main memory. You do not have to worry about stale data. Keep that in mind as we go through the examples. But for more understanding around memory visibility, watch Java memory model videos in this Java concurrency playlist. The first group is the one you will use most often. It deals with single variables. The most popular member here is AtomicInteger. If you need a thread shape counter, this is your go-to class. The star method here is increment and get. It increments the value and returns the new value in one atomic step. There is also get and increment, which returns the old value first and then increments. And then there is compare and set method, which is the raw CAS operation we just talked about. It takes an expected value and update the value, and only performs the update if the current value matches the expected one. Let me show you a practical situation where this shines. Imagine you're building a system that generates unique IDs for incoming requests. You could use AtomicInteger and simply call increment and get method every time you need a new ID. Multiple threads can call this at the same time and they will never get a same number. No logs, no blocking, just a simple atomic operation. Multiple threads can call this generate ID method at exact same time and they will never get the same number. There is also AtomicLong, which works exactly the same way but for long values. You would use this when your numbers can grow beyond the int range, or when you are dealing with timestamps in nanosecond. Next, we have AtomicBoolean. This one is perfect for flags and toggles. The most common pattern is using compare and set to start a task only once. For example, if you have a background job that should run only when it is not already running, you can call compare and set method. The first thread that calls it will succeed and it will start the job. Any other thread that tries will simply see that value is now true and it will back off. It is clean, lock free. Finally, we have AtomicReference. This one works with object references. It is useful when you have an immutable object like a configuration or a person record and you want to swap the entire object atomically. Instead of updating individual fields, you build a new object and use compare and set to replace the old reference with new one. This way, readers always see a consistent snapshot. One quick warning about these classes, whatever we have seen, they are not suitable as keys in hash-based collections like hashmap. Their equals and hashcode methods are based on object identity and not the actual value they hold. So if you use them as map keys, you might get unexpected behavior. Just keep them as values, not as keys. Now that we know scalar group handles a single variable really well, but what if we have 1,000 counters or 100 product stock levels? You could create a separate atomic integer objects for each one of them. But that would add a lot of memory overhead. There is a better way for that, and that involves arrays. The second group is the array group. Instead of wrapping a single value, these classes wrap an entire array. Let you perform atomic operations on individual elements. The three members here are AtomicInteger array, AtomicLong array, AtomicReference array. The key advantage here is that updates to different indices do not interfere with each other. If thread A is updating first and the thread B is updating third element, they can both proceed without any contention. This makes these classes ideal for scenarios where you have a fixed number of independent counters or slots. Let me give you a concrete example. Imagine you are building an inventory system for a small warehouse. You have fixed number of product IDs. Each product has a stock label. You could use an atomic integer array where an index represents a product ID and the value represents the stock count. When a sale happens, you want to decrement the stock for that product, but only if there is enough stock available. You can do this by reading the current value, checking if it is sufficient, and then using compare and set to update it. If the update fails because another thread changed it in the meantime, you just retry, and this pattern works really well. Notice that pattern here. We read the current stock. If there is not enough, we fail immediately. If there is enough, we try to update it using compare and set. If you look at it closely, you will see we are passing index along with the expected value and new value. That is the change we have while using methods in array group. And now coming back to the code, if that update fails because another thread changed the stock in meantime, we just loop and try again. This is the standard CAS retry loop. For object references, you have AtomicReference array. This is great for managing pools of reusable resources. For example, suppose you have a pool of database connections. You can store all the connections in an AtomicReference array, and each element holds a connection object. You also maintain a parallel Status array may be an atomic integer array where 0 means free and 1 means in use. When a thread needs a connection, it loops through the array, finds a slot that is free, and atomically makes it in use. If someone else grabs that slot in the meantime, the CAS will fail and the thread just moves to the next slot. This is much more scalable than using a single lock for entire pool. So here you can see when a thread needs a connection, it will call acquire connection. It loops through the array, finds a slot that is free, atomically marks it as in use. If someone else grabs that slot in meantime, CAS fails and the thread just moves to the next slot. No blocking, no single point of contention. The common pattern across all array atomic classes is the retry loop. You get the current value at the index, compute the new value, and then call compare and set in a loop until it succeeds. It is simple, it is fast, and scales really well. Arrays are great for structured data. But here is a situation that comes up a lot in real projects. You have an existing class. Maybe it is from a third-party library or it is just a legacy code that you cannot easily change. The class has a volatile field and you want to perform atomic operations on that field without changing the class itself. You cannot extend it to use AtomicInteger directly. So what do? This is where the third group comes in. The third group is called field updater group. These are AtomicInteger field updater, AtomicLong field updater, and AtomicReference field updater. They use reflection to access and update the specific volatile fields on existing objects. Let me walk you through a common scenario. Suppose you have a bank account class. It has volatile int balance field. You cannot change this class because other parts of the system depends on its exact structure. But you need to perform thread SEP deposits and withdrawals. In that case, you can create an atomic field updater for balance field. You do this by calling a static new updater method and passing the class name and the field name. Once you have this updater, you can call methods like add and get or compare and set on any bank account object, and it will atomically update that specific field. The big advantage here is memory efficiency. When you use AtomicInteger, you are creating a separate wrapper object for each value. If you have millions of objects, that adds up. With field updater, you are working directly on existing field. There is no extra object. But the downside is that the field must be declared volatile. If it is not, the updater will throw an exception at runtime. Also, the field must be accessible to the updater, which means if it is private, you have to create field updater inside that legacy class. That basically indicates you must own the class. So here is the clear picture. I have this updater created directly inside bank account class so that I can access its private volatile field. This is the way you can access these fields and set a updater for existing field. Otherwise, you'll get exception. So the key points here is to note is field updater is not a magic tool to break encapsulation in third-party libraries. It's a performance optimization for code you control where you want to avoid memory overhead of wrapper objects. So when to use it? You own the class and control field visibility. You can make the field public, protected, or package private, and you need to save memory when dealing with millions of objects. Now let's see Atomic Reference Field Updater. For object references, you have Atomic Reference Field Updater. This is useful when you need to atomically swap entire objects inside legacy class. For example, you have configuration class with volatile map of string map to string field. You can use this updater to replace entire map atomically with new one. This is common pattern for atomic configuration updates. This gives you the same atomic swap capabilities on existing object fields. The best practice with these updaters is to declare them as static final fields in your utility class. You only need one instance of the updater for the entire application. Creating them repeatedly is unnecessary and adds overhead. So let's quickly recap the three groups. The single value group, which includes AtomicInteger, AtomicLong, AtomicBoolean and AtomicReference, is for simple counters, flags, reference swaps. Use these when you have one variable to protect. The array group, which includes AtomicInteger array, AtomicLong array, AtomicReference array, is for when you have fixed number of independent slots like stock levels or connection pools, and use these when different threads update different indices. Field updater, which includes three updater classes, and it is for when you cannot change the class itself but need atomic operations on its volatile fields. Use this for legacy code or when memory overhead is a concern. If this breakdown helped you make sense of atomic package, consider hitting the like button. It really helps the channel. And if you want to catch the next video, go ahead and subscribe. We are going to dive deeper into concurrency topics and I think you will find them useful. In the next video, we are going to see some atomic classes which are designed for even higher contention scenarios. And if you are dealing with really heavy traffic, you do not want to miss that one. That is it for this video. Thanks for watching and I'll see you in the next one.